mean, it makes sense when I explain it, but I just don't understand like.
Hello everyone. So today we are gonna continue the polar coordinate system, and as you guys recall, I know that you all submitted the quizzes. Some of you, I don't know, didn't submit the quiz on time, so they send me messages. So I will say about that. But if you solved the quiz and submitted the PDF, you are not allowed to submit something else. Like you cannot come later, oh, I found my mistake and I can submit it again. It's not gonna work. There's chances, there's another 3 quizzes. Maybe I would exclude the worst one at the end, so it just depends how the grades look like. But yeah, the quiz is just only open one time, 30 minutes. Try to solve during the 30 minutes, make 2 minutes to scan or take a pictures and then upload it so that you don't have to submit it later. So try next time in the next quiz to plan time for uploading your answer, right? Okay, so today we are gonna continue on the topic that we started last time. We are still working on the kinematics of the particles. Like we are still studying positions, velocity, acceleration, but with different coordinate system. We are done with the Cartesian coordinate system. We did tangent normal coordinate system, and we started, if you guys remember, polar coordinate system where we have r and theta. Try to practice at home. What is the difference between the coordinate system? Try to look in the textbook or solve the examples that I have in my notes on the different coordinate systems. And in the test or in the quizzes or in the exam, I'm not going to tell you what coordinate system that you are going to use. You have to figure it out yourself. Which one that is going to be much better, that solve your problem much easier. Okay? So, in each one of these coordinate systems, there's rules. Like there's position, there's velocity, there's acceleration. And everyone has different formulation. And I told you that there's an equation sheet that has all the formulation for the different coordinate system. So all your job in the quiz is to figure out which coordinate system that you are gonna pick, and then take the equations from the sheet, put it in front of you, and try to find how you can find the quantities that needs for each equation, right? Okay, so last time we had 2 equations for the polar coordinate system. Let's put it here, polar coordinate. Polar coordinates, which is r and theta, and we found that the velocity v is equal to r dot in the u r hat plus r theta dot in the u theta hat, and then you have the acceleration vector r double dot minus r theta dot squared in the u r hat plus r theta double dot plus 2r dot theta dot u theta hat. And we spent like 30 minutes last time trying to prove where these come from. We did lots of integrations, we did lots of geometry analysis, we did like 2 boards to come up with this equation. Okay, so let's find out today how we can solve a problem. We're gonna solve one, and there's another one that I did it from the textbook, but I'm gonna only solve one on the polar coordinate system. So in this example, let me put it here, example. This example is not in the textbook, so maybe you focus with me on how we're gonna do it. It says that you have a bar like this, and this bar is attached to a hinge here, like this, and this hinge is attached to the ground. So you have a ground here, and this is a bar, and this bar has like void in the middle, or let's say, yeah, something like this, and in this, there's a collar here that can move on this axis. Something like this. So this bar is moving from the horizontal direction all the way here, and it start at angle theta equal to 120 degrees. The thing is, look at this movement. You have this bar can rotate, and it start from here. Like this bar is something like this here, and can rotate that way. And in the same time, while it's rotating, there is something on it that can move on this axis. All right? So there's two movement. This bar is moving, rotating, and there's something can move on this axis. So what I gave to you is what is the initial theta that this bar started at, which is 120 degrees. And by the way, the first thing that I would see about this, that's a polar coordinate system. Why? Right now I have a bar that is moving radially. That's a radial, and is not moving, is not a body moving on a random curve that I use tangent normal, and it's not a body that moving XY or a projectile motion that moves in the XY coordinate and the acceleration under in the gravity direction. So usually Cartesian coordinate system used when you have a projectile motion. So this is like a perfect example for a radial coordinate system. Can you guys tell me where is the R and theta for this body? Like if I want to put the R and theta direction, if you guys remember this, like we say, usually if you have a body, let's say this is your XY, and this is a curve that your body is moving on. So R is from the origin to your body, something like this. This is R. So this is the position, and this is the R direction, is in the direction of the R. So this is R hat. What is the direction of theta? Direction of theta is perpendicular to the R, and it is in the direction of increasing theta. So the increasing theta is that way. So is theta that way or that way? It's going up. It is that way. So that is the theta hat. So it is perpendicular to the R, and it's in the direction of increasing theta. Let's apply the same rule to this problem. Where's my body? My body's here. Where's my center is here? Can you guys tell me where's the R direction? From this center to your body, and it's going all the way up. So that is the R hat direction, right? How about the theta? In which direction? Is it going that way or that way? By the way, I'm saying that the body's moving, so it's gonna be this way. That is the theta hat, right? So this is the direction. By the way, this is really, really important. These directions, you have to know them. Where's the positive and where's the negative? Okay, so this is the first step. Second step, I give you that the theta is a changing over time. The time rate of a change of theta dot, is equal to 0.1 radian per second. And also I give you theta double dot, the time rate of a change of the velocity, or the acceleration, or the radial acceleration, is equal to negative 0.04 radian per second squared. So this is the angular position, the angular velocity, the angular acceleration. These are all given. And I give you that R, this R, is it changing? That means that this body is moving that way. And R is it changing with a function R equal to 2 sine theta. So all this is given. And I'm asking you, what is the velocity and the acceleration of this body? What is the total velocity and what is the total acceleration? What is the quantities that we have here? I have R dot, I have R double dot, I have theta, theta dot, theta double dot. These three, I have them. Everything about theta, I have them, but I don't have R or R dot or R double dot. How can I get it? What I'm gonna do? I differentiate R, so let's do it. So I have R equal to equal to 2 sine theta. So let's find your differentiation skills. R dot means I want to find dr dt. All right, that's R dot. Can you guys find R dot? It's gonna be 2. What? Cosine theta, let me find it, it's theta or 2 theta. It is, yeah, it is sine theta. Okay, that's it, or there's something else? Since we are differentiating with a variable different from the variable of the problem, if I'm differentiating this function with respect to theta, like if I'm getting dr d theta, I will stop here. But since I'm differentiating with a variable that is different from the variable of the equation, at the end you have to put d theta dt, right? We agreed to this. If we are differentiating with respect to theta, so this is gonna be theta, which means 1, and I don't have to write it. But right now, this is not the case. I'm differentiating with the time, so I have d theta dt, which is theta dot. All right, so this is actually really easy. I wanna make sure that I'm recording. Okay, we are good. All right, so the next step is much harder. What about the second derivative of r? That means r double dot. It's gonna be a little bit difficult. Can we do it? This is 2 variables. Cosine theta is a variable, theta dot is a variable. The derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. Okay, let's just start. I'm gonna write it here. There's not much space over there. R double dot. Okay, what should I write here? 2 or negative 2? Negative 2 sine theta. I'm not done yet. The differentiation of this is negative 2 sine theta multiplied by theta dot. Theta dot, I didn't look at this yet because this is just the derivative of this part, right? And then multiplied by what is outside. You're gonna say to me, why do you have 2 theta dot? You have 2 theta dot because the derivative of this is negative 2 sine theta multiplied by d theta dt. And then you already have theta dot outside, so basically you can say that this is theta dot squared, right? So this is the first part. The second part is this multiplied by the derivative of this, which is easy. So this is gonna be plus 2 cosine theta multiplied by theta double dot when you differentiate it one more time.
I'm sorry, where did we get the theta dot up there?
Where did I get what?
Where did we get that from?
This
No,
from this.
the theta dot.
This one?
Yeah.
When we differentiated the 2 sine theta, the 2 sine theta give us 2 cosine theta, and
Oh.
then we put d theta dt. So
Which is equal to?
yeah, theta
okay.
dot.
Okay, okay.
All right. So same thing happened here. We differentiated this and give us another theta dot, and I already have one outside, so it makes theta dot squared. All right, so that's the hardest part. Once you are done and you get these 2 derivatives, it is just direct substitution. So if you got your derivatives right, the problem is done for polar coordinate system. So all what I'm gonna do right now, I'm gonna plug in the values. Like right now, I'm gonna plug like, okay, let's find this at, this is gonna be at theta equal 120 degree, so it's gonna be 2 sine 120. 2 sine 120 is equal to 1.73. And this, once you substitute with the theta and theta dot, with the values that is given here, theta is 120 and theta dot is 0.1. So this is gonna give you negative 0.1. And once you substitute here with theta and theta dot and theta double dot that is given here, so you are gonna find that this is equal to 0.0227. All right? So right now I have all the variables that I need, so I can get the velocity vector. The velocity vector is equal to r dot, which is this negative 0.1 in the ur hat, plus r multiplied by theta dot. R is 1.73 multiplied by theta dot, which is 0.1. So it's gonna give you 0.173 in the u theta hat. So I'm done with B. Same thing, you are gonna do it with A. You are gonna substitute it all this. And by the way, that's a lot of variables. So make sure that you have your signs right, make sure that you have everyone in place, And once you do the substitution, you are gonna end up with having 0.0054 in the UR hat minus 0.0892 in the UV theta hat. So I basically substituted every one of these here. So once you come up with the R's and the thetas, you substitute, your problem is done. Okay, does anybody have any questions?
Really?
Yeah.
For in the velocity, that's 1.73 times 0.1?
Yeah,
Okay.
this one. This problem can be harder if I want to make it hard. By the way, this is not hard. Like, because the thing is, you have two equations. The hardest part of it is the differentiation. So if I want to make it hard, I will make this function hard, like the R, this one. Like, let's make it like really complicated equation. Right now, it's only one variable. What if I give you this, like, times tan theta? Two functions multiplied by each other. It's gonna be much harder because once you take the derivative of this, you want the derivative of this multiplied by this, plus the derivative of this multiplied by this. So that's the first one. And you're gonna end up with a big equation with lots of variables, and when you take the second derivative, it's gonna be much bigger, right? But this is a mechanics class, a dynamics class. I'm not testing you in math. I just wanna make sure that you understand these equations. So probably I would give you an easy, simple equation, which can have some x squares, maybe exponentials, maybe, because the exponential is easy. You differentiate it, it is just you drop the number from above the exponential and it's gonna be easy. Sine, cosine, but I'm not gonna go in deep, all right? Does anybody have any questions? Yeah.
So is that 1.75 or 1.7?
This 1.73 multiplied by 0.1.
Oh, okay.
Sorry about that. Yeah.
I know that you say you were gonna make the numbers easy and everything for differentiation of these, but let's say that the question were to instead ask for, like, let's say the question were to instead give us R double dot and theta double dot, right? And we would have to integrate in order to find R dot and.
If that's the case, yeah.
You
But
would
the
also
thing
do-
is, I don't think I would do that, like, because as I said, I'm just testing you in dynamics, so I just wanna make sure that you understand how to use this equation, how to get these variables, how to plug them in here,
Okay.
right? And I believe the hardest part, because if I wanna test you, I will test you how you understand this body, how you understand the mechanics of this body, how you understand where the theta is, or all these stuff. And by the way, we're gonna get back to the same concept in Newton's in the next chapter, chapter 13, because we are learning this, so this can be the basics for forces, because forces multiplied by acceleration. At the end of the day, we're gonna use this acceleration, multiply it by the mass, and get, so maybe I will not test you in this, maybe this is just gonna be a part of a problem, so that you can use the final acceleration to get forces. So, anyway, so this is just basics for now.
Up to what chapter is the first exam? Up to what chapter is the first exam?
I think the first exam will be up to chapter 13, so.
Up to the end of 13.
Depends on how far we are gonna get. The midterm, I believe, the spring break is the last week of February, right? So I believe it's gonna be before the spring break. So we still have like three weeks from now or something. Okay, is that fair enough?
Do you do practice exams?
Well, the exams is, like, when I said the exam, I look at the textbooks that I have and I try to find some problems there. I will take it, change numbers, and just put it on the topics that I have. If you basically can make exam yourself. Like, you can pick some questions from each topic, and I will tell you the topics, like, you know the topics that we got. We can, like, questions from the topics that we covered and put them together. I can do this for you, like, I can make 2 exams for you. One of them is easy, one of them is difficult, but basically look at the textbook.
Okay, thank you.
All right, so let's now talk about the last part of the chapter 12, which is dependent motion. Is the course difficult so far? Do you guys have any? Well, it's a difficult class. Like I wouldn't, like when I would take this in my undergrad, it was one of my most difficult because it has lots of math, lots of physics. But I try, like I'm doing my 100%, I try to make good notes for you, try to make problems easy for you. Maybe my pace is a little bit fast, but the class is recorded, you have the notes, you have everything, because we have a lot of content to cover. And by the way, I don't cover, because this class has part of fluid dynamics, so we had to take some topics from the particle and rigid body dynamics so that we can cover some fluid dynamics, and you have a visit to the wall of wind that we might plan after the spring break. So we have lots of stuff to cover. That's why I'm recording the class for you. If you missed something or if there's something that you need to go on, if you have any issues, so that's it. But think about it. This is basics for engineering. I'm not sure what classes that you guys take right now. If you targeting to be a structural engineer or something, this can give you the sense of engineering of bodies. You learn Newton's second law, you learn dynamics, and this can help because we also are gonna cover structural dynamics. So if you wanna be a structural engineer at some point, this class is gonna help you. And even if you wanna be in the water engineering, there will be part of fluid dynamics that you are gonna learn. So I would recommend, what year are you guys in? Is that are you most of you senior, juniors? You have 2 years to graduate, right? So take this as a chance because you guys 2 years are gonna be outside building some buildings or collapsing. So I don't know what are you guys gonna do, but the thing is, take this as a chance to learn because you only have 2 years to be an engineer, and this is your last chance to get knowledge unless you are gonna go for an advanced degree or master's. So if you are gonna go, let's say this is your last 2 years, so this is your last chance to learn. And after that, maybe you will not have time to read or to go back to the topics that you learned. And the more that you learn and the more you are gonna be good at what you are doing, the more people are gonna want you. So even if you did your master's, the more you are gonna good and get good grade and get more knowledge, the more finding job is gonna be easy for you because you are gonna go to the job interview sitting in front of your interviewer and you will know everything. You know even maybe more than him. So that's gonna be the case. And if you are good in what you are doing, maybe you will not have to apply for jobs. The jobs is gonna come to you. That's what happened with good people. If you are good in what you are doing, if you are very, very good, if you know more knowledge than your peers, that any graduate know, if you, I'm gonna teach advanced structural analysis, or I'm gonna teach in structural dynamics. If you're oh, this topic is really good, and I wanna know how structures is responding to earthquakes or wind, and you start reading a book, or you start doing extra effort, and when you go to interview and he see what you have, definitely he's gonna want you. The competition is high, there's many of us, but when you are good in what you are doing and you know it very well, and actually I know that the grades is what the employers are looking at, so this is something that you need to be careful to have really good grade, but having more beyond that, knowing more knowledge, proving that you are trustworthy and you know knowledge more than your peers, that is really good for you. So I would if you have 2 years to graduate, try to use these 2 years to get as much knowledge as you can so that when you graduate, so you can be easy to find job. And even you can find job in places in big companies, not a small company. I'm talking about Acom, ARM, Stantec, McKinsey. So all these big companies, they don't take anybody. So you need to have you need to prove yourself. So that's what I want to say. Anyway, so let's get back to dynamics. So right now we are going to talk about dependent motion. So for dependent motion, it's an application of the particle dynamics. So dependent motion. So let's say that I have pulley system. So I have something like this. We usually use the pulley system to lift things, all right? So you can lift things with less effort. So I have a pulley system like this, that, and and you have a cord from here and go all the way around here and go that way, and then it wraps around this pulley and goes all the way out. And you have a weight attached to this, and you have a weight attached to this. So this is, let's say, A, and this is B. So you have a bunch of connected particles, and I would give you, for example, the speed of one of these bodies. I would tell you, for example, I'm gonna have this one is moving with velocity v2, and please find what is the velocity of body A. Okay, let's agree on something. If this body is moving down, B, with a velocity v2 going down, this body is going up or going down? It's going up. It's gonna go that way. So this is v1. So let's find out how we can find the velocity v1 if we know v2. So that is what we call dependent motion. The motion of this body is dependent on the motion of this body. The way to find this, it's only one rule, that the length of this cord, doesn't it change over this process? The length. The length doesn't change, right? If you pull this body down, the length of this cord doesn't change. It's just getting long somewhere and getting short somewhere. It's just like you are pulling this with one force, somehow you are converting these into two forces to pull this body. So the length of this doesn't change. So the way that we do it, we find a specific fixed datum. Like, for example, I'm gonna pick this as to be my datum. And I'm gonna measure the length from this datum, because I know that this point is fixed and this point is fixed. They will never move, right? And I wanna find the length of this cord at here. So I would say that this is equal to y2, and this is equal to y1. Why I only picked these two lenses? Why I didn't pick this lens? The thing is, I know that this lens is variable, right? This can go up or down, and this is variable. How about this lens? Does this lens change? Constant. How about this here? There's also part of the cord here and part of the cord here. It's still constant. Yeah. And this part also constant, never gonna change. The part on top here. Everything, all the changes happens below this data. This is the change that happened. Can you guys tell me the length of this cord, if I told you that this, all this from here to here is equal to L1, and this part is L2. So the length of all this cord is gonna be, let's just start from here. It's gonna be equal to Y2 plus this part plus this part, which is L1, plus, what is this length?
That's Y1.
Y1. Plus there's also a part here, I'm gonna call it L3. Plus this part L3, plus another Y1, plus a L2, right? All this should be equal to constant, which is the length of the cord. But I know for sure that this length doesn't change during the motion. And the length under this pulley doesn't change. It's gonna be always there, if it goes up or it goes down. So this part of the length is gonna be always there, and this one is there. So all these are constant. Let's say, I'm gonna write it that way, y2 plus 2y1 plus l1 plus l2 plus l3, all this is equal to L, which is the length of the whole cord, right? I'm gonna take the derivative of this equation. Let's take dt of this equation. It's gonna be dy2 dt plus 2 dy1 dt plus, what is the differentiation? How much is this length is it changing over time? 0, right? Because it's constant. And this one is constant, and also L3 is constant. So all these is gonna be 0. How about the length of the whole cord is it changing during the motion? It's constant, right? So all these are gonna be equal to 0. So right now we were able to build a relationship between V2 plus 2V1 equal to 0. Y2, the time rate of a change of this length is the velocity of this body. The time rate of a change of this length is the velocity of this pulley which attaches it to this body. So if this is moving up 1 meter per second, this body is gonna move 1 meter per second. This is moving 1 meter per second down, this is gonna move down 1 meter per second. So right now we were able to find the relationship between the velocities of these two bodies. For example, if I told you that V2 is equal to 3 meter per second. So basically, I would be able to find that V1 is equal to V2, negative V2 over 2, which is gonna be equal to negative 3 over 2, which means negative 1.5 meter per second. So if this body is going 3 meter per second down, so this body is gonna be equal to 1.5 meter per second up. They have an opposite sign, right? Did we all got that? Okay, let's solve a real problem that is a little bit difficult.
The weight of A and B doesn't matter.
The weight is what? The weight what?
Are they, do they have the same weight, A and B? It doesn't.
Well, I'm just putting a body here. Like, we're only looking for the velocity. And the weight is gonna matter when we study forces. So when we study forces, so the weight is gonna affect this velocity, but I did all the math and I told you based on this weight and this weight is gonna give you this velocity.
Could you quickly explain how you got the V2 plus 2V1 equals 0?
Alright, so first I tried to find the length of this cord and try to find what is the variable lengths and what is the constant lengths. So I have this as variable and these two are variable which are equal to each other, and they are gonna be always equal because this is gonna go up and it's gonna make them equal. What is constant? This part around here and the part around the buckle here and the part top here. This is gonna be constant at any motion at any time. So I tried to list all of them, either they are constant or variable, and then I tried to group them. These are the constant and these are the variables and these are the constant. Then I differentiated this equation with respect to the time, because if you have displacement or if you have length and you try to find the change of the length over time, so you want to get velocity, you have to differentiate over time. So I differentiated the whole equation with respect to the time. This gives you ui 2 dt, which is the velocity of this body. The time rate of the change of this length, that means how much this body is moving up or down. Same thing y1, but L1, L2, L3, and the whole length of the cord, they are all constant. So if you differentiate it, then they are going to give you zeros.
Okay.
So that's why this is equal to 0.
Okay, understood.
Well, wouldn't Y1 also be a constant since it's not really changing
Y is
in length?
constant.
Y1, because
Y1?
it's not changing in
Well,
length.
well, the thing is, if you pull this down, this buckle is going to go up. If it goes up, that means that Y is it changing with every displacement that B is making down.
Okay.
So, and that's actually the concept of whole lifting things. That you would put, you have a very heavy weight here, so you pull it with one cord and you give the forces to two cords so that this body can move up. It's gonna move it slowly, but it's gonna move.
Okay.
Alright, and so I got here some steps to solve dependent motion problems. I told you identify fixed datum. Like what I did, this is the fixed datum, and it has to be fixed. Like you cannot bake the datum here at this point. If you bake the datum here, this datum is moving every single time. And then get the variable lengths within the same cable. Like you might have two cables, you cannot mix them together. So within the same cable, try to find the variable lengths. I know this is variable. And the thing is, we can neglect the constant lengths. Like we can neglect we can actually merge all these and we say, oh, they are constant. We can put them as a constant because constant 1 plus constant 2 plus constant 3 equal 1 constant, okay? And
And at the end of the day, and you can add this constant with another constant, is gonna give you a third constant. So you can basically send these, all of them out, and you say that these are equal to constant, right? Like if I send this, and this, all the way to the other, and I put them, they are all equal to constant when?
You mean L?
Yeah, because think about it. All what happens here, this length, if this length go up, let's say 1 meter, this body is gonna take the 1 meter and go 0.5 meter. How? Because he gets 0.5 here and 0.5 here. Let's say that this went down 2 meter, so I take 1 from here and 1 from here. So that's what happened. This length plus these two lengths are gonna be equal constant, because you take from this and you give this, or you take from this and you get that. That's what happened with like the pulley system. Does anybody have any questions? Any more questions? So what I mean by y2 plus 2y1 is equal to constant is that, like, if this body move up from here to here, so basically this is gonna get this piece and this is gonna get this piece, and that makes sense. You see, this was 3, that became 1.5. If this is 6, this is gonna be 3. It's gonna be the half of this piece. So they have a relationship that their lenses are constant. If one is getting long, the other two are getting short. Okay, so, and the second step that I told you about is to take the time derivative of the equation that you built. Like, you found out this equation, this is the hardest part, is to find this equation. Once you find it, take the derivative so that you can convert it to velocity. And then the third part is to do some equations manipulation. Like, if sometimes you're gonna have 2 cables, you're gonna have 2 equations. Sometimes you're gonna have 3 cables, you have 3 equations. And we're gonna see this in a little bit. So let's solve another problem. Like, let's say I have look at this system. I have one cord. It starts from here at this center and go all the way up, and then wrap around this pulley and go all the way around and wrap around this and go and stop here. That is the first one. The second one is start where this ended and go all the way up and wrap around this and go all the way here and wrap around this and go this and then come from here, and then you are having a load B here, and I give you that this body is moving up with VB equal to 1 meter per second. And I have a body here alright, and all these 3 points are at the same line. Okay, the first step is to find a fixed datum. Where is this fixed datum? Same thing like the one that I did here. So Where's the fixed datum?
The point
The
of
quarter.
three wheels of.
At this 3 point, these 3 pulleys are lined up here, so this is a fixed datum that I can measure the variable lenses from.
Can you
All right.
spell that out?
Hmm?
Fix it,
What did you say?
I don't know how to spell that.
Spell what? Fixed datum?
Yeah.
Datum is like baseline. D-A-T-U-M. Alright, so I have this, and let's name the bodies. I'm gonna name the moving bodies are this, and this. These are the 2 things that are moving in the air. There's nothing else that's moving. You're gonna tell me, oh, this body's moving too. Yeah, it's moving, but it's attached to this one. So they are both having the same speed. So basically, I can call this B, and I'm not sure how did I name it. I named them 1, 2, 3, but let's call this B, and this is A, and this is already named B. So let's actually track the movement. If this body's moving up, what is gonna happen to this? It's gonna move up or down?
Down.
Down, and what is gonna happen to this? Down too, because all the system is gonna collapse little by little. Alright? So let's actually go to the next step. Try to measure lenses from the fixed data. So from this data, I have this point here. I'm gonna call it, this one is Y1. And to be consistent with the notes, I'm gonna call it Y3. And this one with the notes, it is Y1, I guess. Alright. And then, this is the moving bodies. I'm trying to find where they are from the data. It doesn't matter what chord it is, I wanna know how much they are moving with respect to the data. And it has to be the same base that you are measuring to. You cannot make another base, so because we are gonna relate them to each other, so they have to be related to the same base. And this is the third one, I'm gonna call it Y3. But let's not mess inside, and we can put it somewhere outside. I'm gonna put this here. I'm gonna call this Y3, and I'm gonna call that this body's moving up with PV equal to 1 meter per second. Alright, let's build the equations. Let's subtract the moving lengths of each chord. Yes?
Didn't you call the right length Y3 as well?
This?
Yeah.
This is Y, oh, sorry, this is not Y3, I'm sorry. This is, because I already called Y3. So this is gonna be Y2. Okay. Do you still have the same question?
No.
Okay, because I thought that I didn't name Y3 yet, so I thought that this is Y2. But the thing is, this body at a different elevation from this body at a different elevation from this body. You can name them whatever you want. Like you can name this Y1. The thing is, I want to be consistent with the notes. All right? But you can name this Y1 and this is Y2. But at the end of the day, you know what you are doing.
The 2 or 3 line?
Which
Y3, is only the 2 or 4?
Y3? Y3 is here, like is measuring this body, the center of this body. And Y2 is measuring from the center of this body, and Y1 is measuring this body. Okay? Alright, so let's find the length of, you only have 2 equations. Why? It depends on the number of chords that you have. If you have 2 chords, that's 2 equations. 3 chords, 3 equations. 1 chord, 1 equation. Why? Because we know that all the chord length is constant. This is how we build our equation on. So I know this length from here to here is constant, doesn't it change? So let's get this length. This length starts from here to here. This is a variable length. It's equal to Y3. The thing is, I have another Y3, right? From here to here, that's another one. So that is gonna make it up to 2Y3. All right, I get this piece and this piece. You are gonna tell me, how about this piece here and this piece here? These are gonna be always constant. They are not gonna change. All right, so we can make left-hand side and put all the constants here. You're gonna tell me how we get this? This constant is gonna be the length of the chord minus all the lengths that you wanna put. L1 minus L2 minus L3 that were here. Like you have an L here and L here, you are gonna send them to the other side. All right, so this is where the constant comes from. But we right now are only interested in the variables. So I have this and I have this. Do I miss something else that is variable?
What about like the part?
This
between-
part?
Yeah.
This part, this is variable because it keeps changing. How can we find the length of this part? Can you guys, from these variables, y1, y2, y3, tell me what is the value of this part?
Y3
y3 minus what?
Y2.
Minus y1 or minus y2?
Y2.
Y2, right? Because this minus this is gonna give us this, right? So it is, this is plus y3 minus y2. So this is gonna give us 3y3 minus y2 is equal to constant, and that is the first equation. You are done with 50% of the problem. That's chord number 1. Let's get to chord number 2. Yeah, go ahead.
Oh, never mind.
Let's get to chord number 2. Chord number 2 is start from here and goes wrapping around these pulleys and goes down like this. So from what I see, this length is constant and this length is constant. The only variables is this, 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 and this. Can you guys tell me what equations that I can use here? How many of these?
3.
3. 3y1 or y2?
Y2.
3y2 and plus or minus, I'm gonna add more, right? So plus, there's a piece that is this part, which is y1 plus y1. Equal to constant. Where is this constant? This constant actually equal to the length of the whole chord minus this piece and this piece and this piece, right? So this is all equal to constant. So, alright, I'm done with the first step, getting the equation. Second step, differentiating this equation with respect to time. So that's very easy. Basically, you are gonna say that 3v3 minus v2 equal to 0, and 3v2 minus v1 plus v1 equal to 0. It is the same equation. You are just gonna convert y's to be velocity, and any constant is gonna be 0, right? Does anybody have any problem? Same equation, because when you differentiate this is gonna be velocity, and any constant is gonna be 0. So this is your two equations. If you know the velocity of v, this is really, really important. I need you to focus on this. Vb is going up with 1 meter per second. However, when I measured y, it was going down. That means if you want to put Vb is equal, that means that V1 is equal to negative 1 meter per second. Why is that? Because y1 is measured from here down. So the positive should be going down. If the velocity is going up in the opposite direction of what I assumed, that means that the V1 is equal to negative. And this means that 3v2 minus 1 equal to 0, so v2 equal to 1 over 3 meter per second. So I got the velocity of this body, body number 2. This is body number 1, and this is the body number 2. So that means the body number 2, if this is going up, this is gonna go down. Because y2, the direction, the positive direction, is going down with 1 over 3 meter per second. So if you have V2, you can come to the other equation to get V3. So basically V3 is equal to V2 over 3. And this is gonna be 1 over 3 over 3, so it's gonna give you 1 over 9 meter per second. Okay? And that's actually makes sense. Why? This is one chord is giving to 3 chords. So if this one chord is going up by 1 meter per second, this one is gonna be divided into 3 pieces. And this 3 pieces is gonna be equal to 1 3 meter per second going down. And this 1 over 3 going 3 meter per second going down is gonna be divided into another 3 pieces, 1, 2, 3. So basically, the velocity is higher and getting slower and slower as we move from chord to another. So you make the motions dependent on other motions. You guys got that? Is it difficult? By the way, I believe it's one of the simplest problems in this class, this one. It's basic equation, doesn't have any differentiation, doesn't have anything. All what you need to know is to track the chord. And and try to make a base and try to measure the variable lengths, and try to make an equation based on the length of each chord, and then solve the two equations together based on the information that is given to you. Right, so let's solve another one. Yes.
How can V3, like how does V3 end up positive? Like everything is going down besides P.
B is positive and B is going down. And A is going down. They both are go down and this is going up.
Yeah.
So when this line goes up, all this is gonna get loose and keep going down. This one and this one. Up is the negative, down is the positive. Because I measured this from here to here.
Okay.
If you say that the length, the thing is, you cannot measure from here to here because this is the variable. Alright, so all these are moving with respect to this one. So the next example is example 12. 21.
We're not gonna get, V3 over there?
We're not gonna get what, D or V?
V.
We got V3 here. V3 is equal to 1/9 meter per second. So I substituted in the second equation, this V2 that I got, it gave me V2/3, so it's 1/3 over another 3, it gives you 1/9 meter per second here.
I didn't see it, I'm sorry.
No worries. Okay, so this one is really easy. Problem is, drawing these problems is a little bit difficult, so. I have a body like this. B. And this body is attached to Alright, so here you have body A and body B, and I told you in this problem that body B is moving up with VB equal to 6 feet per second. And it's one chord. One chord goes from here to here, to here, to here, so it's only one chord that is moving with 6 feet per second. So what we need to find out, I need you to find out what is the velocity of body A. So this is a little bit tricky. You will be like, oh, so right now I have two moving bodies. I have this body and I have this body are moving, and I only have two chords. So that means two variables in one equation, right? So the thing is, we need number of variables equal to the number of equations. Here we had three. We had like 1, 2, and 3. So we had three equations. We had two chords, and we have three variables, but I gave you one of them. The thing is, this one, I put these, we call this as guided support. The guided support guide this motion that makes this body is always going up, not like making like this. So if this one is gonna go up, this one is gonna go up the same way, and we are gonna go up together. So the velocity of this body is equal to the velocity of this body. Like if this one is moving 1 meter per second, this line has to move 1 meter per second, and this whole entire body is forced to move 1 meter per second. So why? Because they are attached with a constant core that they move up together. So basically, I only have one pulley that is only moving. I mean, like that has variable length, and the variable length here is the same like the length here. So I can say that this is my datum here. All right, and I want to find what is the velocity of this body. I want to find this. If I found this, let's call this as YA, and I have this as, this is Y, let's say call it YB, and this is YA. All right, so if I found the velocity of this body, I can find the velocity of this body because they are equal. Okay, so how can I do this? So I'm gonna look at this chord. This chord is going that way, that way, that way, and that way. The thing is, during this motion, if this body is going up, these two are gonna be always constant. If they are here, or here, or here, they don't change. What it changes is this lenses. Like this pulley can go up and down. Like once this go up, so these lenses are gonna go up. So basically your equation is gonna be equal to 1 YB plus this, plus this, plus this are equal to constant. So you have 3 YB plus 1 YA equal to constant. How? So the total length of the chord is equal to YA plus constant plus YB plus constant plus YB plus constant plus YB plus constant plus another constant, because this part is going to be always constant with the motion. So here you are going to have 3 VB plus VA are equal to 0. So I already gave you that VB is equal to 6, so 3 multiplied by 6 plus VA are equal to 0, so VA is equal to negative 18 feet per second. And that makes sense because once this is gonna go up, all these 3 lenses, 1, 2, 3, are gonna add more lens to here. Okay? So that is the final answer for this one, and this is really, really direct question. Does anybody have any problem? That means 18 feet per second, that means it's going, oh, sorry. VB is going up. Well, I got the answer right, but it shouldn't be negative. It should be positive, but I should have put VA here. The 6 VB is negative. Why? Because VB is going up and YB is going down. So that means that this is negative 6 meter per second. We agreed that Y is positive down, so if the body is going up, it's going to be negative. So this is negative 6. So that means that positive 18, which is the positive is going always down. All right. Okay, so did you guys got the concept? I have a bunch of examples solved here. Maybe you try these other two because definitely the midterm or the next quiz is gonna be on the pulley system. So I'm gonna make an announcement with the next quiz, maybe on Tuesday. So I'm gonna say what topic it's gonna be, either this or either the tangent normal or the polar coordinate system. Well, I might not say what topic exactly. I might say it's a chapter 2, and for example, if you got a quiz in this, I might not get it in the midterm and get another something because you already got listed on this. All right, so with this, I believe chapter 12 is done, except a sub-chapter, it's called relative motion. I'm not gonna cover this chapter because it's kind of like, I'm not gonna do a lot of application on this, and we need to have some time for the fluid dynamics part and for the structural dynamics part. So I believe that's enough for chapter 12 for now, okay? So right now I'm gonna start a little bit of introduction about chapter 13. chapter 13 is about particle kinetics. And when I say kinetics, that means we are looking at forces and moments. Kinematics, we are looking at position, velocity, and acceleration. So basically, this whole chapter is based on Newton's second law of motion. And this law is like, it's an empirical equation which was verified experimentally, and by applying a known unbalanced force to a particle and then measure the acceleration. Like you put a force on a particle, and you measure the force, and you measure the acceleration of the particle. And you put another force, and you measure the acceleration. And you try to plot the force with acceleration, how does it change? They found out that there is a relationship between the force and the acceleration. The more that you are gonna put force on the body, the more the acceleration is gonna go up, right? So they are proportional. And they found that the proportionality factor is the mass. So that is the Newton's second law. And sometimes we describe that the force is the time rate of a change of the linear momentum. Like if you want to find the velocity on a body, you find the linear momentum. Momentum is the mass multiplied by the velocity. So if you found that the time rate of a change of this quantity, you are going to get the force. And that makes sense. Usually the mass is constant. Like if the mass is constant, you can take it out of the derivative, and you are going to end up with dv dt, and this is equal to the mass multiplied by the acceleration. But by the way, some problems have a changing mass, like the mass will change over time. Let's say that you have a rock, and this rock is falling downhill. So the rock, when it started, it has a big mass, and as it falls, it keeps like getting cracked, and the mass keeping changing over time. So if the mass is changing over time, so you have to keep it inside the differentiation, and you have to differentiate the mass with respect to the time. But usually the mass in most of our problems are constant, and we can take it out of the integration. All right, and it says that Newton's second law, this is Newton's, this is the core of this whole chapter. This law doesn't apply for high velocity bodies, like velocities that approach the speed of the light. Like if you have really high velocity, this one doesn't apply. And also this law doesn't apply for particles that are really small in the size of the atoms. The atoms needs their own systems and their own equations, so this also doesn't apply. So high velocities, it doesn't apply. Very small mass at the size of the atoms, this doesn't apply. So, and this is going to take us to talk about a really interesting topic. It's called the Newton's gravitational law. So let's talk about Newton's gravitational law of attraction. Newton's discovered that two bodies that has masses, they always attract each other. The masses attract each other. Like if somebody at the end of the room, and I'm here, there's attraction, but this attraction is really small. When this attraction becomes high, when one of these masses are really big, like the mass is huge. And that's actually what happened with gravity. When you try to jump out of the ground, the mass of the Earth grab you down because it's huge with respect to your mass. Same thing with being on a moon or being on Jupiter or whatever planet out there. The more the mass is, the more the gravity is going to be. So that's why the gravity on Mars is different than the gravity on the Earth, because it has different mass. So same thing, if you are on a big planet, like that's actually what the scientists say, like if you are on Jupiter or something, that's much way bigger than the Earth, so the gravity on this planet is much higher. So, and Newton's at that time say, like, if this is the mass of the Earth, and you are trying to jump or something, or to go on Burj Khalifa and let a body go down. So let's say that this is a mass m, and this is the mass of the Earth. This is the center center of the Earth, and this is the radius of the Earth, and the mass of the Earth is ME, and this is your masses. And that's actually how we can gauge the weight of the bodies. Like the weight of the bodies is the force that the Earth exerts on your body to grab it down. That's why you multiply the mass by G. So there's a distance here between the body and the Earth, which is really, really small considered to the radius of the Earth. The radius of the Earth is equal to 6.378 multiplied by 10 to the power 6 meter. So let's say that you are throwing your body from Burj Khalifa, which is 800 meter or something. That's nothing with respect to the radius of the Earth. So basically, the center between these two bodies here, and you have, I drew it a little bit higher just to show you, but this is not the actual distance. So basically, this delta can be neglected. Like I can say that this is equal to 0. So basically, if you are jumping from the ground, the distance between the center of your mass is equal to r. Because this distance, let's say it is equal to d. R plus d is always going to be equal to r because d is really, really small. You see how much we did the rounding here? We rounded to the kilometer at 8. So if you have 800, it's not going to show up here in this number. So the gravitational law is saying that the gravitational attraction between any two bodies, the gravitational attraction force between any two bodies is equal to a constant is named as the universal constant of gravitation, and this is equal to G multiplied by the mass number 1. Let's actually put it in a general term. M1 multiplied by M2 divided by R. That is a general rule. The mass number 1 multiplied by the mass number 2. If you want to find the attraction between two bodies, go R here, the distance between them, with the mass number 1, mass number 2, and multiply by G. And G actually is a number that is really, really small. 666.73 multiplied by 10 to the power negative 12, and the units is meter cubed, kilogram second. So if you try to find the attraction between two bodies that are really, really small, and you multiply by this number, so you will find that the attraction force is really, really small. When this attraction forces become big, when these masses gets bigger, and this radius gets smaller. Okay? So this is how he discovered the weights of the body. The attraction force between a body that you throw it from the ground and you want to find the weight of this body, W, or right now our F is going to be equal to W. I'm going to see the body that has mass M and how the Earth is grabbing him down, which is the weight, is equal to G multiplied by mass number 1, which is the mass of my body, multiplied by the mass of the Earth over the radius of the Earth. So this is how you can find the relationship. Then they found out that if you multiply these numbers, like if you did the mass of the Earth, M Earth is equal to 5.97 multiplied by 10 to the power 24 kilogram. If you try to find these values, and this is the R of the Earth, it's going to give you G. So this is going to be M multiplied by G. So if you want to find the gravitational acceleration on any planet, you have to multiply the universal constant of gravitation by the mass of the planet over the radius of the planet. So this is how you are going to find the ground acceleration of this planet. Okay, so the more the mass of the planet, the more the gravitational acceleration is going to grab you. The smaller, the less the gravitational acceleration of this planet is. So basically, this is the final rule of that. And this is where W equal to mg came from. So anybody, when you throw it from the ground, there's a gravitational acceleration. It's going to grab him based on his weight, and this weight is equal to the mass of the body multiplied by G. G is equal on Earth, like sometimes, I don't know, I'm not gonna do it, but like, let's say we're solving a problem on the moon, we're solving a problem on Mars, so this G is gonna be different, okay? Alright, so that's it for now. Next time we're gonna continue on this topic. See you guys.